So today I want to talk about the NPN transistor. Understanding the transistor is essential to unlocking, the foundations of digital electronics. Even though most electronics are going to be done with field effect transistors, I like to introduce the BJT transistor as it's commonly used in analog and digital. And it gives you kind of I personally feel it's the harder of the two to learn. So if you can kind of understand how the BJT transistor works, you can be a little bit more comfortable with field effect transistors and so forth, the kind that is used in CMOS technologies. BJT transistors are the building blocks for TTL logic. TTL logic is what gives computers the ability to do what they do, make very simple decisions, store memory. So with the transistor, all right, first thing we have to understand is when I talked about it in the lesson, I kind of took it in terms as if you were baking something, okay? Like this is a cookie sheet or something, and you're gonna bake yourself a transistor, because in reality it's not too far-fetched of an analogy. Basically, to make a transistor, you use a material that has one extra electron in the valence ring, making it an N-type or a negatively charged ion, and then you take an element that has a deficiency in that valence ring or a positively charged ion, and you kind of make yourself like a little sandwich. So if this was a top-down view of a baking sheet, you take a little N-type material, you take a little P-type material, and then sandwich it with some more N-type material. So when you put these together, and you have to correct me if I'm wrong, it's been a while since I've taught this lesson, but N-type material being like arsenic or something, P-type material being, I want to say, boron, and then more arsenic over here. You can use any element as long as the N-type material has 5 electrons in the valence ring and ready to give one of those up, and that your P-type material only has 3, or deficiency to make that 4. Atoms like 4 valence electrons. It's a nice stable number for the atom. So everything we do about electronics is exploiting what we know about electrons, atoms, and the foundations of that type of chemistry. So what happens when we put them together? All right, when we put an N-type next to a P-type material, the electron excess from the N-type material jumps into the holes of the P-type material. And I'll draw little holes here. All right. So as these P-type holes start to get filled with these electrons, these are no longer positively charged ions. In fact, they kind of have an excess, because the boron by default, or the P-type material, in case I'm incorrect on that, now has an extra electron. So now, because it has an extra electron, it's like a barrier. It doesn't need any more. It starts to repel. So as these electrons start to fill the holes in these P-type material, a barrier starts to form, which is represented by these red markings here, and that happens on both sides. Okay. So as soon as enough electrons are in there, then the barrier exists, and this is without any type of outside influence. No voltage has been connected to either the collector, the base, or the emitter, which are the 3 parts of a BJT transistor, and the barrier exists. Okay, so as you know, or if you've worked with transistors before, these are designed to flow electricity or flow electrons from the emitter to the collector, meaning under normal bias, you'll have a positive voltage up here, and actually, you guys probably want me to do that in red. Let's do that in red. You'll have a positive voltage up here, and you'll have a negative down here, okay? Or a less positive voltage. So the idea is that this positive voltage is going to entice or attract electrons to move from the emitter through the base, through the collector, and out. So electrons want to move in this direction toward the positive voltage. However, since there is a barrier potential that exists here at the base, the electrons will get to this point and become stuck. Okay, so there's a barrier here that this has to get through. All right, now it is possible to put a strong enough of a positive bias here that it will just literally drag electrons through the transistor, but it was not designed to operate as such. And in fact, there is a rating on the particular type of transistor that you use that tells you what that voltage is. However, to use it between saturation and cutoff, meaning the maximum flow and the minimum flow of electrons, we have to operate it appropriately. Okay, so it was designed to act like this. And actually I'm going to pepper in a few more electrons just for symmetry there. Alright, so we have this little roadblock right here that has to be overcome for the collector to be able to pull electrons from the emitter up to itself. Okay, and that's controlled by the base. Okay, so here's how we control that barrier potential. If electrons jumping from the N-type material to the P-type material are creating the barrier, then we have to find a way to get rid of those electrons. If we can get rid of those electrons, we can shrink those barriers and then flow will gradually increase. So this is why it operates as such. If we increase the base voltage to a positive, or put any type of positive voltage on it, guess what's going to happen? Electrons are going to start to filter out of this P-type region and go toward that voltage at a rate of speed dependent upon how much voltage we put there. For instance, 1 volt is going to attract a few electrons, but 3 volts will pull out 3 times as many electrons. Alright? So the more electrons we pull out of this center region, e.g. the higher the voltage we put on the base, the thinner these barriers are going to be. So if we were to vary the base current, like we kept it at a positive voltage, but if we go up, down, these barriers essentially are going to increase, decrease, increase, decrease according to the base voltage. Alright, which is going to cause your collector current to increase, decrease, increase, decrease as well. Alright, so this is why I like to say that you're using a little current to control a big current, or little brother is telling big brother what to do, because there are more electrons that are capable and ready to flow from the emitter to the collector straight across the transistor than there are out of the base. Okay, the base, you're just trickling a few electrons out of the P region, but in doing so you're controlling the barrier within the transistor itself. So this is basically how the transistor works. Primarily a good explanation for amplification circuits. However, you can also use it in TTL if you put it into saturation or cutoff. So operating it in saturation or cutoff is simple. It's much more simple than this previous explanation. It's putting a voltage that's so strong on the base, or that's strong enough on the base, that the maximum amount of current is allowed from the emitter to the collector. Okay, so it's putting enough current on, or putting enough voltage on the base so that these barriers shrink next to nothing. You're at saturation, the maximum amount of flow is going from the emitter to the collector, and then to cut it off, you just remove that voltage. You take that voltage off the base, now it's in cutoff, now you have no electrons that are flowing. Okay, so saturation maximum, cutoff, no flow. So the reason that is akin, I guess, to digital logic is because when you're in saturation, basically you're running the max current, which could be representing a digital 1, for example, or you could be in cutoff, which is representing a digital 0. So for instance, say you had a small piece of electronics, let's say like maybe a Arduino or Raspberry Pi, that you want to drive a motor. Alright, so there's a pin on the Raspberry Pi, but you know that the Raspberry Pi doesn't have enough current in and of itself to drive that motor, so you can't connect that pin directly to the motor because it would drain the Arduino or drain the Pi. So we hook it up to a larger transistor with a larger current. So the Arduino controls the base, and when it needs to kick voltage up, and say we put the motor across the transistor or in series with the transistor, we could put it either place. I'll just put it down here. So say we put a motor down there. So now when the Arduino kicks it into saturation, or basically when it applies a positive voltage here, this thing starts to flow, the motor kicks on, and then when it goes to zero or takes that little bit of voltage off of the base, then that circuit goes to zero. Current flow goes to zero, the motor stops. So that was a little bit of explanation as to what a transistor is, how it can be used in digital electronics, and a little bit of the science behind it. I'm RL with Digital Bytes. We'll see you next time.